Does isotope analysis prove that we're made to eat meat and that we've been eating meat for 2.5 million years? Hello everyone, I'm Tom Zanton, and today I'm going to talk to you about isotope analysis. And to start with, I want to say that this is something that people say all the time. That I hear all the time. Isotope analysis proves that we're made to eat meat. All these populations were eating meat. Going back to 2.5 million years ago, Homo habilis was eating a lot of meat. Isotope analysis proves it. So, first of all, what is isotope analysis? So, when we do this isotope analysis, the basic premise of it is that you have these elements. Usually, people talk about carbon and nitrogen. You have carbon, and some of the isotopes are carbon-12, and some of them are carbon-13. And then you have nitrogen. Some of those isotopes are nitrogen-14 and nitrogen-15. And the reason why using this isotope analysis can give you an idea of what someone was eating is because during metabolic processes, you have your body will favor using the lighter isotopes, carbon-12 and nitrogen-14, rather than carbon-13 and nitrogen-15. So for metabolic processes, you use a lot of carbon-12 and nitrogen-14, and to lay down muscle and collagen, those tend to accumulate with carbon-13 and nitrogen-15. So if you're looking at an animal's muscle or collagen or bone or something, and it has more of these heavier isotopes, then that suggests that they were eating a lot more meat because the heavier isotopes bioaccumulate up the food chain, just like mercury bioaccumulates up the food chain in fish. These heavier isotopes can bioaccumulate up the food chain in other animals, especially if you're eating meat. Then you're going to have more of the heavier isotopes. So that's essentially what isotope analysis is and what it can show. But the problem that I have with using this isotope analysis to say that we're made to eat meat is that usually people say, well, isotope analysis proves that Homo habilis 2.5 million years ago was eating a lot of meat. And I don't know, if you had said isotope analysis proves that Homo erectus was eating a lot more meat about 2 million years ago, I mean, I could kind of see it because they were bigger and they had arms adapted for throwing and legs adapted for distance running, and they had better tools and they had bigger brains. But no, we tend to say that Homo habilis 2.5 million years ago was eating a lot more meat. But Homo habilis was barely smarter than a chimpanzee, about the same size as a 7-year-old, with arms adapted for climbing, legs not adapted for running fast or running long distances, and they had the large teeth and guts indicative of a plant eater. And they didn't really seem to have any special adaptations for scavenging or meat eating in general. So to say that this isotope analysis proves that going back as far as Homo habilis, they were eating a lot more meat, that makes me kind of question, is there something that we're missing with this isotope analysis, something that's confounding the data and skewing our interpretations of it? So I looked up what are the limitations of isotope analysis, and there are a few. One of them is, and there are a few more than this, but these are the ones I want to talk about. One of them is sample size. Is the population that you're studying a large enough sample to get a representation of the group as a whole? In theory, it's possible to have so small of a sample size that you say, oh, okay, well, one individual was eating a lot of meat, but that doesn't necessarily say anything about the rest of Homo habilis. That doesn't seem to be an issue here. There seems to be, from what I've read, there seems to be a sufficient sample size that people are confident that the data is consistent and that it's showing what we think it's showing. That they did have heavier isotopes build up in their collagen, So we don't have to say, oh well, it's just one person. No, it seems to be a large enough sample size. Another limitation of isotope analysis is if you don't have a good baseline for what those isotope ratios should be. That can be a problem. Essentially, you need to look at the same time and the same place. So if you're looking at Homo habilis 2.5 million years ago in East Africa, you need to have some other animal that you're looking at from the same time and the same place and compare the two, and then you can say, okay, well, this one was probably eating more meat because it had more of the heavier isotopes. And we do have that. Again, this doesn't seem to be a problem with the isotope analysis. We do have Australopithecus from the same time, same place as Homo habilis, and there's a clear difference there. There's a clear difference between what Australopithecus seemed to be eating and what Homo habilis seemed to be eating. And the last limitation that I want to talk about of isotope analysis is physiological factors. There can be physiological factors that influence how this plays out, and one of those factors is some of those factors are age, stage of life. So if you're in a growth phase, if you're really young, you're growing, or you're in puberty, that can be different than if you're mature, you're an adult, or you're old. And another physiological factor that can affect this is fasting. If you're fasting, then that can influence these isotope ratios because fasting will induce a process called autophagy, self-eating, where your body basically breaks down old cells, recycles the parts, and then uses them to make things new again. Autophagy is great, even though it sounds like self-eating sounds like it might be bad, kind of like if you picture Spaceballs, Pizza the Hut, he ate himself to death. That's bad, but in your health, autophagy is good. So if you have a lot of autophagy, then if you're recycling those materials, every time that those old materials go through metabolic processes, then again they'll favor the lighter isotopes, leading to the heavier isotopes accumulating in tissues. So theoretically, if an animal were undergoing a lot of autophagy, theoretically it could affect isotope analysis by kind of mimicking being in a higher state place on the food chain, because you're recycling a lot of old materials, and every time they go through the metabolic processes, you're preferentially favoring lighter isotopes, and the heavier isotopes are being accumulated within the tissues. So autophagy, I think, can mimic a higher state in the food chain and affect your reading of isotope analysis. So then the question is, would there have been a way that Homo habilis would have been undergoing more autophagy than contemporaneous Australopithecus? Is there some reason why they would have undergone more autophagy? Now, I don't think that they were starving. I don't think that they were fasting any longer than normal. But there are some other factors that I think are relevant that could have caused increased autophagy within Homo habilis. And we need to remember, at the time, at the time of Homo habilis, something pretty interesting happened. The Earth got cooler and drier. The Earth was cooler and drier, but East Africa probably still would have been hot. So East Africa was hot and dry. And you probably know what happens more often if you're in a hot and dry environment. Well, wildfires happen more often in a hot and dry environment. So I think that this is an interesting piece of the puzzle to say, okay, well, 2.5 million years ago, it looks like Homo habilis was eating more meat, but they didn't really have adaptations for it. But they were living in an environment where there would have been more wildfires. And I think they were eating a lot of root vegetables, and I think Australopithecus ate a lot of root vegetables. And so the question is there a plausible alternative explanation to this isotope analysis showing that we ate more meat? And I think there is. I think if some of the things that can cause extra autophagy are a lower protein diet and a lower nitrogen environment. And I think those are both interesting because root vegetables tend to be lower in protein, now not deficient in protein, lower in protein. So root vegetables are lower in protein, and burned habitats you would expect would be lower in nitrogen. Why? Because when there's a wildfire, most of the minerals in the soil, most of the concentration of minerals in the soil actually goes up. Sodium and iron and calcium and iodine, all these things, their concentration goes up in the soil. The main exception to this is nitrogen. During a wildfire, a lot of the nitrogen is volatilized into the atmosphere and lost. So just like if you plant corn on the same field too many years in a row, you need to replenish the nitrogen either with fertilizer or with nitrogen fixing legumes like soybeans. A wildfire can deplete the soil of nitrogen as well. So if we were to say, okay, well maybe a population of Australopithecus started taking advantage of the increased root vegetables that would have been available in and around burned habitats where it would have been a lower nitrogen environment, maybe that could have mimicked a lot of the states of fasting, which could have led to more autophagy. And I didn't mention this, but why would there have been more root vegetables available for Homo habilis? Because the more and more wildfires there are, the more that plants would want to store their energy under the ground rather than above ground, because energy under the ground is safer from the wildfires. So at this time, most likely, more and more plants would have been storing energy underground in the form of root vegetables, and the environment in general would have become a lower nitrogen environment. Both of these two things, if you assume that they were maybe eating more root vegetables and different types of root vegetables, potentially, and they were eating them in and around these burned habitats where it would have been a lower nitrogen environment, both of these could have led to autophagy. And on top of that, if you look at our gut bacteria today, one of the things that our gut bacteria can actually produce is acetate, and acetate can also lead to autophagy. So there are reasons to think that Homo habilis eating a different diet in a different environment, a slightly different environment, still the same general place, but a slightly different environment than it would have been before the wildfire. You can see how there's, I think, a plausible explanation for why they would have been undergoing more autophagy, even on a plant-based diet, than Australopithecus would have if Australopithecus was eating the same foods in the same types of environments and tending to avoid the burned habitats more often. I think this makes sense if you, maybe it makes more sense to say, okay, well, the heavier isotopes indicate a high meat diet. That makes more sense. Maybe by itself that makes more sense. But when you consider everything else, you consider, okay, Homo habilis didn't have a lot of traits that line up with meat eating. We have no good reason to assume that Homo habilis could have acquired meat easily, or that they would have been safe as scavengers. Scavengers need to be able to escape really well. That's why most of them are birds or really fast, agile land animals. And they also can eat a lot really quickly. And like Homo habilis probably wouldn't have been able to do any of these things. And they didn't have good weapons. I don't know why we would assume that they were scavengers, why we would assume that they were hunters. I certainly don't think that. And I don't know how we would assume that they got a substantial amount more meat. But if we assume that they were eating more root vegetables, different types of root vegetables in burnt habitats, which it would have been switching to probably a slightly lower protein diet and a lower nitrogen environment, that could have caused more autophagy. And that could have mimicked having a higher place on the food chain, because you would have been recycling all those old proteins, and every time they undergo metabolic processes, the lighter isotopes would have been favored. More and more of the heavier isotopes would have been laid down in collagen or muscle or bone or other tissues. Like I said, I think this explanation is more consistent with the traits that Homo habilis had at the time. I also think it's more consistent with the configuration of our stomachs. Yes, we have strong stomach acid, which would be useful for scavenging, but would also be useful, I think, for eating root vegetables, because the bacterial load under the ground is much higher than the bacterial load above ground. So if you switch to a diet of root vegetables, then it would also be useful to have a strong stomach acid. And incidentally, wild pigs, which, yes, eat some meat, but they eat way more root vegetables than meat, they also have higher stomach acid than your average herbivore. And I know they're not herbivores, but they still have strong stomach acid, which, I don't know which came first, the strong stomach acid, and then they started eating more meat because they could handle it better, or they started eating more meat and then they got strong stomach acid. I don't know which one came first, and I don't know how we're going to say that which one came first. But I think it's plausible to say that wild pigs, because they also eat a lot of root vegetables, which would have a higher bacterial load, could have a strong stomach acid for that reason. And humans, we have strong stomach acid, but we have small stomachs. Carnivores can sometimes hold up to 25% of their body weight in meat in their stomach at one time. That would be the equivalent of me eating like 38 pounds of meat in one sitting. That would be totally absurd. Like, I could never ever do it. I could only if I wanted to, I could only eat a few pounds of meat at one time. I can't see any good reason why, if you're a scavenger or a carnivore, why you wouldn't want to have a large stomach that could cram just tons of food in it at one time and then just sit on it and digest it. But we don't have that. We have strong stomach acid and small stomachs, which I don't think is in line with being a carnivore or being a scavenger. On top of that, humans have have a lot more salivary amylase, starch digesting enzymes in our mouths, than most other herbivores and other primates, and definitely more than most carnivores. Like lions have none. They have no ability to digest starch from salivary amylase. And I think this is consistent with an explanation for why we would have the isotope signature that we do. If you say, well, we ate a lower protein diet in a lower nitrogen environment, and that's what caused additional autophagy, which mimicked a higher place on the food chain, I think that's consistent with the fact that we have more salivary amylase than other animals, a better ability to digest starch, especially cooked starch, from the digestive enzymes in our mouths. And when we got that, salivary amylase just happens to line up with a large increase in brain size in human evolution, the switch from Homo erectus to Homo heidelbergensis. And if you say, oh, well, we ate a lot of starch, then we got a genetic mutation that allowed us to digest starch better. Then we got bigger brains. That makes perfect sense. If you say we didn't eat starch, we ate meat, starch was just like a backup food, then we got a genetic mutation enabling us to digest starch better, but we didn't really eat a lot of it, and then we got bigger brains. That doesn't really make a lot of sense. Also, I think once you move down to our guts, I know I talk about this all the time, but our gut bacteria are made to eat root vegetables. We have, when you have a baby, their gut is colonized redundantly with bifidobacteria, this one group of bacteria. A newborn baby will get it from the mother's vaginal tract, gastrointestinal tract, and from the breast milk itself. And on top of that, the breast milk feeds it to a ridiculous extent, such that 90% or more of an infant's gut, a breastfed infant's gut, will be loaded with this one group of bifidobacteria, human-specific bifidobacteria. And this has been called the gold standard of a healthy microbiota. This is the healthiest time for our guts in our entire lives. And people who keep more bifidobacteria tend to be healthier and live longer. And bifidobacteria does not just eat breast milk, although it eats breast milk incredibly well, but bifidobacteria also eats starch and inulin and lactic acid bacteria. And I'm sure you know that starch is found in abundance in root vegetables. Inulin is a type of fiber found in abundance in root vegetables. And lactic acid bacteria is the type of bacteria that grows really well on fermented vegetables. When you ferment vegetables, you fill up a jar with water and you pack it with salt and then you stick the vegetables in there. You do that so that it's an anaerobic environment and so that there's extra sodium, because that's where lactic acid bacteria grows really well. And I can see an argument for how that would be pretty similar, actually, to the environment underneath the ground in a burned habitat, because burned habitats, the wildfire increases the concentration of sodium in the ground. Like I said, nitrogen's volatilized off, but most other minerals are increased, including sodium, and it would be an anaerobic or microaerobic environment, not a lot of oxygen. So you would assume that on these vegetables, in this condition, there would be a lot of lactic acid bacteria. And it seems so convenient that human-specific gut bacteria that's colonized redundantly, fed ridiculously well by breast milk, happens to eat the same food, happens to eat all the ingredients of root vegetables, starch and inulin, and the type of bacteria that would be probably growing on it. And that's whether the bacteria is alive or dead. If you give someone lactic acid bacteria probiotics, their bifidobacteria actually goes up. And that's whether the lactic acid bacteria is alive or dead. And in these studies, usually they're heat-killed lactic acid bacteria. So that would be representative of cooking something with lactic acid bacteria on it. But theoretically, going back to the strong stomach acid, those lactic acid bacteria would probably feed bifidobacteria or somehow help them thrive, whether they were heat-killed by cooking or, say, bathed in a 1.5 pH solution like our stomach acid. And then when you do feed the bifidobacteria starch and inulin and lactic acid bacteria, then they produce a number of nutrients for you, like B vitamins and amino acids, some of the very amino acids that might be a little bit low on a diet centered around root vegetables. Not absent, not deficient, but a little bit low. And the gut bacteria will also help you convert plant-based omega-3 fatty acids into DHA, the kind you need in your brain. It will help you convert vitamin K1 into vitamin K2. And it will help you produce more short-chain fatty acids like acetate, which will lead to more autophagy, which is very healthy for you. I think the whole thing, it all just seems to me at least, it seems to all tie together in a way that whether you're in the carnivore camp or the vegan camp or the Mediterranean camp, kind of in the middle, no matter what other diet you adhere to, I don't think that you can explain all these changes throughout human evolutionary history and the human body. I don't think you can explain them as well if you don't start with the assumption that we're made to eat root vegetables. I don't think anyone else can explain these the way that I'm explaining them. Obviously, that's debatable. I'm sure a lot of people will disagree. But if you keep listening to me, I think you'll start to agree. The last thing I want to say is this idea that eating more root vegetables, maybe different types of root vegetables, in burned habitats with the right gut bacteria could have led to this isotope signature where it appears that Homo habilis was a meat eater when realistically, when actually maybe they were eating, like I said, root vegetables in burnt habitats with the right gut bacteria and performing more autophagy and then mimicking being in a higher place in the food chain. The last thing I want to say that I think is consistent with it is that the longest lived population in the world in recorded history were the people from the island of Okinawa in Japan on their traditional diet. Not what they're eating now, but what they were eating a little while ago. When it was recorded, they were eating 20% of their diet came from grains, 10% came from beans and other vegetables, 1% came from animal foods, so they were not vegan, but they were eating a very small amount of animal foods, and 69% of their calories came from orange and purple sweet potatoes, root vegetables, and these were the healthiest people in recorded history. So when you look at it all together this way, I think there's a plausible explanation here for how our isotope analysis could be confounded by autophagy, which could have happened in this certain context in human evolution at the time of Homo habilis. And to me, it all makes sense much more than any other camp. And I don't know if people will agree, but I think it's probably at least worth exploring because a lot of the parts of it do make sense. Even if you disagree with me, you have to say, okay, well, some of these things do line up, so maybe it's worth exploring. Even if you don't agree with me, I hope people will consider this as at least possible, and we can all look into it, and maybe I'm wrong, but I think I'm right. So I gotta stop there, because I know I tend to ramble. So I want to thank you for watching. If you like the video, please like and subscribe. If you have a comment or a question, or you want to tell me that I'm stupid, please feel free to do it in the comments. I look forward to it. And lastly, most importantly, I want to remind you to always eat your root vegetables. Thank you.